Okay, thanks to Hongying. I'm LiYuHao Li from Peking University. I'm very honored to be here to present some of our new results, the recent development for the incentive ratio in BitTorrent resource sharing networks. So the joint work is with Professor Yu Cheng from Suzhou University of Science and Technology and Professor Xiaotie Deng from Peking University. So comparing with the traditional client-server model, I would like to introduce a recent resource sharing model, the peer-to-peer network, called P2P network for short. Here are some features of P2P network. Peers can communicate with each other directly through some connections, and the peers are co-equal nodes. All peers pool their resources in a decentralized system, and the peers can exchange their resources in this system. So this is a client-server model, and this is a P2P resource sharing network. So the idea of this work is from some bandwidth sharing systems. The well-known BitTorrent system is a successful example of P2P file sharing network. The BitTorrent proposed by Cohen is a communication protocol for peer-to-peer file sharing, which is used to distribute data and electronic files over internet. So this is a brief introduction from Wiki. In 2019, BitTorrent was a dominant file sharing protocol and one of the applications that generate greater traffic on the internet. So how does the BitTorrent work? It is a file sharing network. There are some files in some users in the network. Each file is divided into some segments called pieces. When a user wants a file, he will seek out the pieces in the network. Other users will use their upload bandwidth to upload these pieces. These pieces can be downloaded non-sequentially. No need to download from the same person. When he collected all pieces, he downloads the file. Of course, he should also contribute his upload bandwidth to upload some pieces. And BitTorrent is mainly a bandwidth sharing idea, but with the rapid growth of the wireless and mobile internet, there are some more applications of exchanging resources over networks. This actually goes beyond the P2P bandwidth sharing idea. So the P2P network is modeled as a resource sharing network. The resources are shared among multiple interconnected peers. Each peer is both a supplier and a consumer of resources, which is in contrast to the traditional client-server model. The great example is BitTorrent. The resource here can be bandwidth, processing power, disk storage, etc. And the utility is total resource received, and the incentive is to gain more utility. All of us want to download a file as soon as possible, right? So formally, this bandwidth resource sharing system is modeled as an undirected graph G with weight profile W. And each vertex represents a peer or an agent. WV is the amount of divisible resources that agent V owns. Maybe we can see this, maybe this resource can be seen as the upload bandwidth. Gamma V is the neighborhood of agent V. XVU is the amount of resource agent V uploads to its neighbor U. And OX is the resource allocation. So naturally, this bandwidth resource sharing can be modeled as a pure exchange economy. Each player sells its own goods to its neighbors. Each player is also a buyer of goods from its neighbors. And the utility of V is just the total resource he received. So it is actually a special kind of arrow-double market, but on networks. So one may ask, why does the BitTorrent run successfully? Or in another aspect, one of the most important things in the resource sharing is how to allocate resource fairly and efficiently. there is a key technique called the tit-for-tat strategy. Agents may prefer to send resources to peers that send resources back to them, which encourages fair trading. So Wu and Zhang modeled this tit-for-tat strategy as a proportional response dynamics. This dynamics runs like this. At time zero, all agents divide its resources equally to his neighbors. And at time t+1, the amount of resources that agent V sends to you is proportional to the amount of resources he received from you over the total resource he received at time t. And this dynamics has a very nice property. The theorem says the proportional response dynamics converges, and it converges to a market equilibrium. So market equilibrium is an important notion for characterizing efficient allocations in exchange economies. The market equilibrium has two parameters, the price vector P and the resource allocation. The first condition is market clearance. Every agent should sell out all of its resources. The second is budget constraint. And the second is individual optimality. Each player is optimally happy for its resource allocation at the current price. So we can get an allocation from the market equilibrium. Here is an example of the market equilibrium allocation, which is actually a proportional response allocation. For example, if we focus on the vertex V, the total resource he received is 9 units, 4 from U2 and 5 from U3. So he will give back 4 over 9 of its resources to U2 and 5 over 9 of its resources to U3. He will give nothing to U1 since U1 gave nothing to V itself. So this proportional property is applied for every vertex. So this proportional mechanism has many nice properties. It can ensure proportional fairness. It is also efficient because allocation is actually a market equilibrium allocation. But in practice, agents are rational and strategic. It is also important to analyze whether the proportional response mechanism provides incentives for agents to follow this distributed mechanism. So our work focuses on the robustness of the mechanism from the algorithmic game theory perspective. So in this distributed system, here are some private informations. The neighborhood of agent V and the weight of agent V. So correspondingly, here are some cheating methods. For example, the age deleting strategy, weight misreporting strategy, and the civil attack strategy. This talk, we would focus on the civil attack strategy and analyze its incentive. So what is civil attack? In a P2P system, civil attack is a grave threat and subverts the security of network by creating a large number of identities, using them to gain a disproportionately large influence. So this is an intuitive example. If we join in a P2P network, we don't want that almost all of our neighbors are civil nodes, right? So this is a civil attack strategy. Informally, an agent creates several fictitious nodes connected to its neighbors, with its resources assigning among them. So in previous example, agent V receive 9 units of resources, and if V split itself into V1 and V2, and the weight of V1 is epsilon. The weight of V2 is 3 minus epsilon. Then it will get about 11 units of resources, which is strictly greater than 9 units of resources. So the proportional response mechanism is not truthful against such a threatening strategy. But we should not just stop here. We can continue to ask, can we characterize the extent to which a player's utility can be increased by such a strategic behavior? So here is a concept called incentive ratio. The concept of incentive ratio was proposed by Ning Chen, Xiaotie Deng, and Jie Zhang in 2011. Formally, it is defined as the factor of the largest possible utility gain that a participant can achieve by behaving strategically over the original utility when it plays truthfully under a given mechanism. So for our proportional response mechanism, agent V can split itself into several fictitious nodes and assign its resources among them. So the incentive ratio of the proportional response mechanism is defined as the maximal factor of the strategic utility over the truthful utility. We want to show that the incentive of any agent is limited under the CPU attack. That is, the incentive ratio of this mechanism under the CPU attack is bounded by a constant. And here are some past results against the CPU attack. First, the incentive ratio of the proportional response mechanism for CPU attack strategy is exactly root of 2 on clicks and exactly 2 on trace. It means the exactly means the incentive ratio is upper bounded by a constant, and this bound is tight. There is an example can achieve this upper bound. So further, the incentive ratio of proportional response mechanism for CPU attack is lower bounded by 2 and upper bounded by 4 on rings. And this upper bound is improved by 3. But there is a reasonable conjecture that the incentive ratio is bounded by 2, and this bound is tight for any general networks. But there is a still gap between the lower bound and upper bound on rings, and there has been no result on the general network. So why should we focus on the ring structure? Intuitively, it is a very simple structure, right? So here is the importance. Let us first see the figure. This is a very simple example for the CPU attack on rings. The agent V gets 10 units of resources in the original network, and the 10 units of resources is from U2. He gets nothing from V1. After the split, V split itself into V1 and V2, and all the resource allocation is reserved. So now we want to reallocate the resources on V1 and V2. So let us first decrease the weight of V2 into 5, and the U2 will give less to V2, so about 8.57. And then we will increase the weight of V1 to 5. So during this increasing process, U1 receives more from V1, so U1 will returns more to V1. So U1 will give less to U2, and U2 will returns less to U1. Finally, U2 will give more resources to V2. And actually, in this example, V1 gets all resources of U1, and V2 gets all resources of U2. This is why the CPU attack works. Actually, if this means on the ring structure, if we place a CPU attack to split several nodes, it may be still they may be still in a connected component, and if we just increase one fictitious node, but there may be many fictitious nodes whose utility increase, and this is the most difficult thing. In general, this is also the most difficult when we want to prove the general network results. So here are our main results. The first theorem says the incentive ratio of this mechanism against the CPU attack is at most 3 on any general networks. It is the first constant result on general networks, and we tighten the incentive ratio on rings, showing that it is exactly 2. So this is one of our main techniques to prove this result, called resource reserved binary split. In the original network, here is a market equilibrium allocation. So if we split one vertex into two vertices, and the whole allocation is reserved, then the new network, the allocation on this new network is also a market equilibrium. So it is very easy to understand, but the proof is not trivial. And since the allocation is reserved, the vertex of the utility of each vertex is reserved. So here's a direct corollary. In a resource sharing game, the maximal of incentive ratio of agent V through CPU attack can be achieved by splitting into D fictitious nodes. Each neighbor of V is connected to exactly one node, where D is the degree of V on G. And the next lemma is very powerful. Informally, it says if we just adjust the weight of one vertex, then for any set containing V, the utility of the difference of utility of S is upper bounded by the difference of the weight changes. So we can imagine if we just increase the weight of one vertex, then all fictitious nodes, the utility of all fictitious nodes is upper bounded simultaneously. So that's why we can get the 3 on the general networks. So let me just skip the numerical example. And finally, our recent work proved that the conjecture saying the incentive ratio of this mechanism against the CPU attack is exactly 2. And this proof is really hard but interesting. So I wish I can introduce the nice result in a few months later. So combining with 2 truthful results, we proved the robustness of this proportional response mechanism. And here are some future works. First, are there any other attacks deserved to analyze? What does the market equilibrium look like when there is a preference? What does the market look like when there is more than one type of goods? And thank you.
Yeah, thank you for this talk. We'll collect questions from audience. The first question is, what is the arrow debut market?
the LW market is there are many agents. Each agent has some type of goods, maybe M types of goods, and they can exchange their goods to each other. And the utility function can be many types of utility function, not limited to linear utility function. So this is a LW market model.
Okay. The second question is, what does the budget constraint mean intuitively?
It is if you have 10 units of money, you can only get some goods. You cannot buy more goods. Things like this.
Okay. Thank you for answering. I think we can end this talk now. And next talk will start at 3 o'clock. Thank you, LiYuHao.
Thank you.